Hello everyone, welcome all. So today we are going to cover the next chapter, which is nucleus. If you remember, we have covered so far the topic atoms, and in that atoms we have tried to cover almost everything. As far as NEET is involved, there are some shortcut calculations are needed. So first of all, let me cover some shortcut formulas in calculating the wavelengths and energy differences in the Bohr model of atoms. Okay, because in NEET we need to do calculation fast. It is better to remember than to waste time in exam, right? Then to waste time in exam, it is better to remember and mega formulas. So first we will discuss some important formulas for energy transition, right? So let us discuss that energy transition. Okay. So first of all, let us cover this transition formulas. What are some of the formulas? And before that, let me write some shortcut formulas for radius also. So radius of nth orbit, remember in a hydrogen or hydrogen-like atom, it is n square by z times this. This is in angstrom. Okay. Remember, let me write all these important formulas. Velocity in the nth orbit is 2.18 into 10 to the power 6. This factor multiplied with z by n. Meter per second, of course. Next, angular velocity in nth orbit is nearly 4.11 into 10 to the power 16 into z square by n cube. Radian per second, that's the unit. Next, let us take the next thing. Time period of revolution of the nth orbit is 1.53 into 10 to the power minus 16. This factor is multiplied into n cube by z square second. Next, frequency. Frequency 6.54 into 10 raised to the power 15 into z square by n cube. Frequency is in hertz. Next, kinetic energy of nth orbit is 13.6 into z square by n square. This is in electron volt. Next, potential energy. Potential energy minus 27.2 into z square by n square electron volt. Right? Like that. Let us keep on writing. Keep on writing all the important formulas. Next, all these are quantization formulas. What about total energy is what we are using in most of the calculations, right? Minus 13.6 z square by n square electron volt. Next, current I. Current of the nth orbit is 41.28 into z square by n cube. Current is in ampere. Okay. Next, 10th, magnetic field due to current in the nth orbit 4.89 into 10 to the power 5. Right, these factors we have to multiply, okay, into z square by z cube by n power 5. Tesla. Next, magnetic moment. Magnetic moment is 3.64 into 10 to the power minus 19 into n. What about Z? Does it depend on Z or not? Magnetic moment. We will check that. Yes, Sam, how are you doing? So today, before we go to the nucleus chapter, I am writing all the important shortcut formulas for NEET. Okay, very important formulas. This formula I will check why Z is coming or not coming. Z should come, I think so. Ferromagnetic ratio, magnetic moment by angular momentum. The nth orbit, that is always same. Charge by 2m, that remains 8.79 into 10 to the power 14 charge by h. So angular momentum, because this is constant, angular momentum is nh upon 2 pi. So definitely I think this magnetic moment does not depend on z. So that means all these formulas are correct. Note that all these formulas shows quantization, the principle of quantization in Bohr's model. Okay, I have written here almost 12 formulas. In NEET, if you can mug up this formula, you can solve question fast. That is the idea. And now I am also giving some more formulas so that quickly within few seconds you will solve the problems. The only thing is that you have to mug up these formulas. You have to remember these formulas. Okay. So let us go to the next. Energy calculations. Energy calculations. Energy calculation. So already I have told that energy of the orbits you will write like this. Let us write energies. First orbit. So first orbit, you know, minus 13.6 z square. Second orbit minus 3.4 z square. Next orbit minus 1.511 z square. Next is minus 0.85 z square. Next is minus 0.544 z square. Okay, this is for first orbit, second orbit, third orbit, fourth orbit, fifth, up to 5 orbit. You have to remember it. Okay. Otherwise, you know how to derive it. Now, what is very important is that when transition is happening, let us say transition is happening to the second to first. Okay. So, what will be the wavelength for this 2 to 1 transition? We want to calculate that. Okay. So, you remember energy transition that happens 2 to 1, you have to subtract this. If you subtract this difference will give you 10.2 z square. Everything is in electron volt, so you don't have to worry about this. Okay. And when you calculate wavelength in nanometer, you know you have to put 1240 by delta E. This delta is in electron volt, so you will get in nanometers. So if you do this substitution here, lambda 421 approximately comes as 121.6 divided by z square, one stroke solution for big problems, nanometers. 121.6 by z square. Immediately you will solve these formulas. If you remember, very important formulas. Who will do the calculation in exam? Within few seconds you will solve that. That is why highly recommended for NEET as well as for JEE. That they are studying this chapter means we have to mark up this. Okay, then let's go for next. Suppose if I go for transition happening from 3 to 1, that means I am talking about Lyman series. Lyman series I am writing. Okay, so next let me write for lambda for 3 to 1. Lambda for 3 to 1, note it is 102.48 by z square. In nanometer, all the wavelengths are in nanometer. No difficulty in that. All these are in nanometers. Okay. Similarly, lambda for 3 to 3 to 2 transition happening, 3 to 2, 3 to 2, this transition lambda 3 to, this is lambda 3 1. Okay, so lambda 3 to 2 transition, this note 656.1 by z square. Z square, why z square? Because it may not be hydrogen, it may be hydrogen like. Okay, next. What about transition to others? So similarly, lambda 4 1, lambda 4 2, lambda 4 3. Better remember, lambda 4 1 is how much? 97.25 by z square. Lambda 4 2 is how much? 486.3 by z square. Lambda 4 3 is how much? 1876 by z square. All mug up. Solve question fast, mug up. Solve question fast, mug up. No other way. Lambda 5 1, lambda 5 2, lambda 5 3, lambda 5 4. Mug up. 5 1, 94.97 by z square. 5 2, 434.2 by z square. 53, 53128.2.3 by z square. 4052.3 by z square. Again, mug up. All these are in nanometers. Nanometers. Done. Done. Okay, so up to this much, that means what? Again, let me summarize what you need. You can calculate, I'm not saying, no doubt you can calculate, but better remember it. So 2 to 1 transition, then then 2 to 1, that means for 1 it is coming 2 to 1, 3 to 1, 4 to 1, 5 to 1. This is Lyman series. Then you're going to 2, 3 to 2, 4 to 2, 5 to 2. Maximum you take 5, minimum you take 1. Okay. Then uh, then you have to go to 3. 3 if you want to go, then you go from 4 to 3, 5 to 3. Then if I have to go to 4, 5 to 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 formula is better remember that. Okay, right? So here I have taken starting from 5. Starting is 5. That means 5, 1, 5, 2, 5, 3, 5, 4. These are the 4. Previously I have written starting from 4. Starting from 4, 4, 1, 4, 2, 4, 3. Starting from 3, 3, 1, 3, 2. Starting from 2, only one possibility, 2 to 1. So these wavelengths, better remember that. This formula which is given. Otherwise, we know how to derive. Okay, done. Then what else? One of the important thing is that collision, excitation by collision. That one topic is there in NEEV previous year. It has come. It can come. So let us discuss that topic before we go into Nucleus. Excitation by collision. Excitation by collision. Suppose this is a hydrogen-like atom. This is nucleus. This is the atom. Let us say mass of this atom is capital M. And there is a particle. This particle can be anything. This particle can be neutron. It can be proton. It can be electron as well. Or it can be alpha particles. Alpha particle, etc. Any small particle. Okay. It is moving it is going with some kinetic energy. And assuming that this atom is at rest, it may not be at rest, but assume that it is at rest. So, assuming that it is a head-on collision, head-on collision. So, what will happen if this particle is going to collide with this? And you know collision theory, what happens, right? In collisions, there can be perfectly inelastic collision where E is 0, where maximum loss of energy happens. Then there is inelastic collision where some loss of energy happens. And there is perfectly elastic or simply elastic collision where there is no loss of energy happens. Right? So these are the three types of collisions. That same type of collision can happen here. So now important thing is that the loss of energy that is going to happen, that loss of energy will lead to the electronic transition, right? So that loss happens. That loss will generally what happens when two bodies collide? Where is the loss of energy going? Loss of kinetic energy, where it is going? It is going in the form of heat. Two bodies collide and loss of energy happens. It goes in the formation of heat, right? But in case of small particles here, that loss of energy will be captured by the electrons, and electrons will go in the excited state. Okay. So now let us take here some case, that assume that case 1, that this kinetic energy of particle is less than excitation energy. So assume that electron is in ground state. So where it can excite? Minimum it can excite to the first excited state. For first excited state also, if this cannot do, then it will not have any loss. Okay. So if you assume that the energy of this particle which is moving, it has a small energy, not sufficient energy. Let us say we are considering first excitation. So first excitation means 1 to 2. 1 to 2 transition happening from 1 to 2. That means kinetic energy is even less than that. In this case, what happened? No absorption of energy will happen, no loss will happen. So no loss of energy happens. No loss of kinetic energy. No loss of kinetic energy. And you can say that it is perfectly elastic. Perfectly elastic collision. Perfectly elastic collision happens. Second case, case 2, if kinetic energy is greater than the first excitation energy, this is first excitation energy, then in that case inelastic inelastic or perfectly inelastic collision may happen because some loss of energy will happen. Why loss of energy? Some loss will happen that will lead to transition, that will lead to electronic transition. Okay. So electronic transition means it can go from 1 to 2, 1 to 3, 1 to 4, anywhere. From the ground state it can go to any other excited state depending on how much this energy is, right? So that's what will happen. And case 3, we can calculate for perfectly inelastic collision. Assume that the kinetic energy, if we apply equality condition here, then it is also possible. Equality, let us keep equality. So if we now talk about the minimum kinetic energy, so the minimum kinetic energy equality condition we will apply here separately, separate case. So in an equality condition, we can say this is perfectly inelastic, perfectly inelastic. Okay, kinetic energy. Now we have to consider kinetic energy greater than equal to. Okay, keep this condition. Kinetic energy greater than equal to. This case is also included in that. In that case, we are now separately taking this case of perfectly inelastic case. We are separately now taking. Okay, we are separately taking that. That means same case we are studying, but we will calculate now. This is the case 3 where we want to calculate minimum kinetic energy of particle. Okay, minimum kinetic energy of particle for perfectly inelastic collision. Case 3 is same as case 2, but there is only special calculation we are doing. That special calculation is we want to calculate the minimum kinetic energy of particle for perfectly inelastic collision. We know that it is perfectly inelastic collision happens, right? In this case, perfectly inelastic as well as inelastic will happen, but we are going to take the case of perfectly inelastic collision. Now for that we want to calculate minimum kinetic energy of particles. So we know the loss of kinetic energy that will happen, loss of kinetic energy. That loss of kinetic energy will convert into the minimum this electronic transition from 1 to 2. Now loss of kinetic energy formula, if you remember, in collision half m by m plus m into u square is equal to, here what is u? U is this particle speed. Okay, this particle has speed u and its particle has mass small. So that calculation we are doing, minimum loss we are taking. Okay, so that delta E12. Delta E12 how much it is? 10.2. Remember 10.2 Z square, because we are taking hydrogen light. This is in electron volt, of course. Okay, this energy is in electron volt. So from here, in general, now if I calculate from here, you know, half mv square is the kinetic energy, which is minimum kinetic energy calculation, and this is m by m plus m. M by m plus 1 is equal to 10.2 Z square into electron volt. Means this energy is in electron volt. So kinetic energy minimum calculation will give 10.2 Z square times m plus m by capital M. Right? Check out this. Right? This is what we need to remember, and also you can remember this 2.10.2 Z square. You can write this as m by capital M plus 1, and this, of course, Z square already multiplied, so this is in electron volt. This formula is a very important formula. In one step in NEET problem we will solve. In one step we will solve question in NEET. Okay. So once this batch is going to be over, now in few days it will be over, right? So what else? After that, I am planning that only test series I will conduct for this TEJAS 1.0 batch. Only test series. That means I will be creating tests, overall test, all chapter cumulative test I will be creating. All right, and you will be writing those tests, and that only paper I will. That means 10 questions I will be discussing that. Okay, every class, and the frequency of classes will reduce, right? So that's what is one of my target, because from now itself you should start crash course. Crash course is not that you have to start after very long time. Crash course you need to start now itself. Okay, now itself you have to start, not that you need to 1 month 2 months before you start crash course. Crash course now start. Okay, so we'll start that revision program. That means we will be discussing the problems. Now other thing also I am planning. Let me see what are the things will come feasible. I will plan that also. Okay, we'll share it afterwards. But this will go on. Frequency of classes will reduce here. Okay. Okay, so this is an important formula. Now take one question, very important question on this model in NEET model questions, ones which have come in PYQs. Okay, let us take that. The question was, A neutron is there. This is a neutron. This neutron is going with a speed v, okay, and it is going to have head-on collision with a hydrogen atom head-on collision, head-on collision will happen. Now the question is, this atom is at rest. This is not moving. Rest. Minimum kinetic energy of neutron for which inelastic, perfectly inelastic collision. They are asking the what is the minimum kinetic energy for perfectly inelastic collision. For perfectly inelastic collision. Perfectly inelastic collision. What is this? Okay. What is the answer for this? Direct formula, one step, answer is over. We got the answer. We got the answer already because kinetic energy minimum formula is this 10.2 z square m by capital M plus 1. The answer is coming in electron volt, and you should note that the mass of neutron, this is the mass of this particle hydrogen, they are almost equal. This is a common idea. All of us know that neutron and proton has almost same mass. Yes, neutron and proton has almost same mass. So you got the, and Z is 1 because it's a hydrogen atom. So 10.2 1 square 1 plus 1 to 20.4 electron volt. One step answer. One step answer. This is what it is. When very long back, once a student asked this question, I had to derive this. I was not knowing. She was a NEET student and she told that, sir, what is this? How to solve this? I told, let me derive it. I derived it and I told this is the formula. Then I told that next time a question comes, within few seconds you solve it. Okay, that is what, because they don't want more calculation. One step you have to solve it like this. Okay, perfectly. But if they want to make question complex and difficult, they will say that it is at not rest. This is also moving. This is also moving. Then you apply collision theory. Collision theory, you know, U1, U2, M1, M2. After collision, V1, V2. What is the loss of energy? You calculate, right? After you calculate the loss of energy, that loss of energy you have to take first electronic transition happening in hydrogen atom. That's the what you will calculate. Okay, so it doesn't matter, you can calculate for that also. So done. I think now we are done with this chapter. We have solved, but still we will be solving more problems afterwards also. But let us start with nucleus. Nucleus is over in your class. Huh? Completed. Okay. Let's start nucleus. See, I am going to write all the important theoretical points because this chapter involves theory where we need to mug up points. We need to remember what can we do. As a student, you have to remember all these points. You have to fill your notes, make all the important points. That is what is required. You cannot skip. We can, if you want, we can skip in half an hour. But the thing is that it is better to write each and every points. You take help of book, read, write, make the lines, all the important things. Okay, so let's start with this. So first thing is that we need to understand about the atom and nucleus. So we know, suppose this is atom, this is atom, nucleus is very small here. This is a very small, nucleus is very small. So first of all we should know that entire 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 mass, almost entire mass of an atom, that means 99%, is concentrated is concentrated at its center which is the nucleus. That means most of the atoms are empty, and whatever the mass is there, atoms 99% mass is concentrated here only. Here everything is empty only. Okay, that's the important point. And radius radius of nucleus is 10 to the power 4 times smaller than that of atom. So nearly, if you see atomic size, atom size comes in nearly angstrom. This radius comes around in angstrom order. And if you take the size of nucleus, this nucleus size comes of the order of femtometer or Fermi. So nearly 1 lakh times smaller, or 10 to the power 10,000 times smaller. Like that almost. Right? Then what else? What about volume? Volume of nucleus is 10 to the power 12 times smaller than atom, because radius is 10 to the power 4 times, so it is 10 to the power 12 times cube of that. Now, what is atomic mass? Atomic mass and composition of nucleus. Composition of nucleus. Atomic mass. What is the mass of atom and composition? So first of all, we must know the unit, atomic mass unit, or simply 1 unit they are using symbol, that is 1 by 12th of mass of a carbon 612 atom. Okay, and this atomic mass unit or 1 unit comes nearly 1.660302 into 10 to the power minus 27 kg. We have to remember this. Okay, in all calculations. And we know nucleus is what? Nucleus has protons and neutrons, and together these are called nucleons. Neutron has protons and neutrons, and together these are called nucleons. So first of all, note that number of proton is equal to atomic number. This is atomic number. Number of uh, neutron is equal to A minus Z. A is, what is A? A is called mass number. Mass number is number of proton plus number of neutron. Okay, that's what we should know. And okay, then how do we represent a nucleus? Representation of a nucleus. A nucleus is represented by a capital letter, here mass number, here atomic number. Sometimes it is represented in the same side. Mass number and atomic number are represented. Okay. Now let us go little bit detail about the protons and neutrons. So let us note about proton. So for proton, we should know that charge of proton, anyway we know charge. What is charge of a proton? Plus E. What is mass? Mass of a proton is nearly 1836 times mass of electron. Okay, and mass of proton If you calculate, it comes 1.0072766 unit. Okay, and also note that proton proton is not used in nuclear fission. Nuclear fission. It is not used in nuclear fission because of positive charge. Because of positive charge. Because proton will get repelled from nucleus, so it cannot penetrate inside. That's the reason they are not used. And proton is stable outside nucleus. Outside nucleus. It is not stable inside nucleus. Why? Because inside nucleus proton will repel. So it is not stable. Similarly, write down some points about neutron. Neutron. Neutron was discovered by James Chadwick. James Chadwick. James Chadwick in 1932. And of course, there is no charge. It is neutral. Neutron is neutral. Mass of neutron is nearly 1839 times mass of electron. So mass of neutron in atomic mass unit is 1.008664 unit. Okay, that's what we should know. All these are theory, but these are very nice theory. We have to remember that. Otherwise, if you don't know these points, then what do we know about nucleus chapter? Okay. Then note about artificial transmutation transmutation of elements. Artificial transmutation of elements. Artificial transmutation means conversion of one element into another by artificial means. Artificial means. Example nitrogen 714, which is stable, is bombarded with alpha particles. These are alpha particles, and when we bombard them, we get oxygen 817, which is also stable, and we also got one proton, which is proton or hydrogen nucleus. So this was the discovery by Rutherford. Rutherford had done this discovery. Okay. Rutherford was the first because he was doing alpha scattering experiment, right? When he was doing alpha scattering experiment, he was trying with not only gold foil, he was trying with different things. So he tried nitrogen and he successfully converted nitrogen into oxygen. That's of course isotope of oxygen. Okay. He did that. So this artificial was transmutation was discovered by Rutherford. And this transmutation artificial transmutation was possible for elements with atomic number that means Z less than 20. Atomic number less than 20, they can use artificial transmutation. And what is the significance of this artificial transmutation? Significance of artificial transmutation, because using this so many discovery happened. Discovery of proton, neutron, all this happened because of this only. Then it also produces radioactive isotope or radioisotopes, and it also produces transuranic transuranic elements. What are transuranic elements? I think heavier elements like those of uranium, right? Uranium, of course, is used in nuclear reactors. So transuranic elements similar to that we can produce using this process, artificial transmutation. Okay, then what else? Let us discuss about the discovery of neutrons little bit. Discovery of neutrons. We already discussed that it was done by James Chadwick in 1932, and he received Nobel Prize in 1935. Because of this discovery, he received that Nobel Prize. Here, important point to note that mass of neutron is almost same as mass of proton, and charge of neutron anyway we know that neutron charge is 0. What was the discovery? Chadwick Chadwick observed Chadwick observed emission of emission of neutral radiation neutral radiation when beryllium nuclei were bombarded with alpha particles which could knock out protons. So what is that artificial transmutation reaction? So take beryllium, you can write this side also 94 plus helium. This is what is alpha particle. Nuclear reaction happens, it becomes carbon isotope, but this is unstable. This is unstable carbon isotope. It becomes carbon C12 plus neutron plus Q. Q refers to energy. So it is like a exothermic reaction. Exothermic reaction is happening. That was the discovery by Chadwick. Okay. So Chadwick was using this experiment, and he discovered that this neutron which he got here, where is neutron? Neutron is coming out here. You see, this is what is neutron. This neutron particles were coming out like a radiation, but he found that these particles does not get attracted by any electric field or magnetic field. That means this is a neutral. This is a neutral radiation. That's what he is talking about, neutral radiation. So this neutral radiation which Chadwick observed is the neutron only. Okay, that's the neutron he discovered. Okay. Then he did the calculations. How he did the calculations? He did the calculations to find out mass of neutron and other things. He applied some conservation ideas. So the neutral radiations consist of photons and all those things were there. Energy of photon would have to be much higher than neutral radiation. Chadwick therefore concluded that neutral radiations are made up of neutron. So if he thought that if this radiation is some photon, then photon energy must be very high. But this neutrons, that energy was not so much high. So from there he could got the idea that it is made up of some particles. And he applied the conservation of mass idea he applied. Then he applied conservation of energy, conservation of energy, conservation of mass, conservation of energy. He applied, and after applying this, he got the mass of neutron. He calculated the mass of neutron nearly 1.00866 atomic mass unit, which is nearly 1.6749 into 10 to the power minus 27 kg. Remember, mass of neutron, if they ask anybody now in this chapter, you must know up to 4 digit. Up to 4 digit you are supposed to know. 1.6749. And what is mass of proton? Remember 4 digit. Oh, how much? What is mass of proton? How much it is? Remember that? You have to remember that. What is mass of proton? Let us write it. 4 digit. Up to 4 digit. What is proton mass? Mass of proton. Let's write mass of proton. 1.6726. Up to that much you remember. Into 10 to the power minus 27 kg. Okay. No. Here you are not going to do that because because in this chapter you need to calculate up to 4 digits, because you have to do the calculations of energy, right? And the energy in electron volt and mass defect calculations will come. In all these places you have to use up to 4 digits. Sometimes they use also 5 digits. Actually, they will give in the questions, so no need to worry about that. But in this case, if they are not giving, so there is a problem. Hmm. Then some properties of neutron. Let us write properties of. Today we'll try to wind up this chapter. How much possible? We'll let us try. Properties of neutrons. So no effect of electric field and magnetic, because it's neutral. So no effect of electric field, magnetic field. Very high, very high penetrating power, penetrating power, very high, sorry, very low ionizing power, stable inside nucleus. Average life average life period average life period is nearly 1000 seconds. Outside nucleus outside nucleus a neutron decays. How a neutron will decay, that is very interesting. So a neutron decay like this way. It will become a proton. It will also become electron, beta minus each electron. Will also give an antineutrino. Very important reaction in NCERT it is given. They may ask this. Okay, outside nucleus, a neutron will decay. Neutron is not stable outside. The spin angular momentum is half h by 2 pi. It is in joules second. Magnetic moment is 9.57 10 to the power minus 27 joule per Tesla. Half life half life is nearly 12 minutes. Neutron shows wave nature like diffraction by crystals. And there are two types of neutrons. One is slow moving neutrons, slow moving. Another is fast moving. Slow moving and fast moving both are capable of both are capable of doing artificial transmutation. They can do artificial transmutation. But the slow moving neutrons, which are called passive neutrons, they are mostly used in nuclear reactions, nuclear fission reactions, because the slow moving neutrons can stay inside the nucleus for longer time and it can create more instability inside the nucleus and then the nucleus will decay. That's why you see the nuclear reactions, nuclear fission reaction, the uranium nucleus is bombarded with the neutrons, and these some of these neutrons are like slow moving neutrons which will remain inside the nucleus and create instability. Okay, right. Okay, then we will study the different types of uh, nucleus. Different types of nucleus. Types of nucleus. So let us start with isotopes. I will classify here isotope, isotone. So many things are there, right? Some of this already you know that, but let us quickly do it. Isotope means Z will be same, but mass number is different. What is example? So many examples are there for this. Lithium 3 6, lithium 3 7, hydrogen itself there are 3, proton, deuteron, triton, right? All these examples are there. Then isotones. What are isotones? Isotones have both A and Z, both are different. But then what is same? The number of neutrons, which is A minus Z, this is going to be same in both the nucleus. So what are some of the examples of this? The examples are nitrogen 717, oxygen 818. You can see the difference of this 17 minus 7 10, 18 minus 8 10. All these are same. Okay. Then next, third, isobars. What are isobars? They have same mass number, atomic numbers are different. They are called isobars. Right? Take example. Example, argon 40, calcium 40 20. Right? Mass numbers are same. Okay. Many other examples are there. Germanium 32 76. Selenium 76 34. Many examples are there. Okay. Next, isomers. Isomers are what? They have AZ, both are same, but they have different nuclear properties. Different nuclear properties. Different nuclear properties. Example, bromine, which has 80 35, and another bromine also same. Then what is the difference? This is metastable state, and this is ground state. How do we know? We have to represent by different symbol by putting M here and putting G here. G means ground state, M means metastable state. Okay, and then last, isodiphers. What are isodiphers? They have Z and A, both are different, but A minus 2Z, which is the difference is number of neutrons minus number of proton. This is going to be same. What are the example of this? Example is sodium and aluminum. So they have A minus 2Z same, right? These are the different type of nucleus. We have covered all this. We need to mark up all this. Of course, in objective questions, they may ask which of them are what, right? Okay, next. What is the charge of a nucleus? Now we are going into nucleus because we have gone first proton, neutron. Now we are going into nucleus. So nuclear charge is equal to plus ZE, that we already know. Nuclear size, nuclear size. The size of the nucleus is given by Rutherford experiment, and from Rutherford experiment this comes as R equal to R naught e power 1 by, where this R naught is equal to 1.2 femtometer or 1.2 into 10 to the power minus 15 meter. A is of course mass number. So if it is like this, then you can say the volume is proportional to, because volume is 4 by 3 pi r cube, so it will be r cube means it is proportional to it, right? That's what you can see. And here you need to note that this nuclear size is of the order of femtometer or 10 to the power minus 15 meters. Actual size of nucleus is less than 4 into 10 to the power minus 14 meters. Actual size. This is a rough estimation of order of the size. Oh, okay. Then what is next? Next, we need to note few important points. That radius is proportional to a power 1 by 3. Area, surface area, is proportional to r square, that becomes a power 2 by 3. And volume is proportional to r cube, that becomes. Okay. Second point to note here is, suppose splitting happens, splitting of nucleus. Heavy nucleus. Okay, very important point. What happens if a nucleus splits? A nucleus may split into two different nucleus, or it may split into more than one. But this application is going to be important. Let us know about this application. Suppose this is a nucleus, mass number A. It breaks into two nuclei with mass number A1, A2, and let us say that initially it is at rest. So it will be moving with velocity v1, it will be moving with velocity v2. We can apply the conservation of linear momentum, because just like explosion of a bomb, right? So a1 v1 is equal to a2 v2. This is mass number, right? Because total momentum is 0. So you can see the velocity ratio is equal to mass, inversely proportional to mass ratio, which is radius r1 r2 whole cube, right? And what about kinetic energy ratios? Suppose this got kinetic energy 1 and it is got kinetic energy 2. So kinetic energy 1 by kinetic energy 2, this ratio half mv square. So mass means a1 v1 square, a2 v2 square. Now a1 by 2, let us write in terms of radius. So a1 by a2 ratio is what? a1 by a2 is v2 by v1. So v2 by v1 into v1 by v2 square. So finally it will come v1 by v2. And v1 by v2 is same as radius cube ratios r2 r1 whole cube. So kinetic energy ratios and speed ratios are the same. Okay, that's the idea. Then next, density of nucleus. Density of nucleus. What is the density of nucleus? Assume nucleus to be a sphere. It is a sphere. So we know density is equal to mass by volume. Substitute mass, right? Mass is atomic mass unit into 1.66 into 10 to the power minus 27. This will come in kg, in volume is 4 by 3 pi. Radius cube, radius is what? 1.2 into 10 to the power minus 15 into e power 1 by 3 cube. Calculate this. Once you calculate, it comes nearly 2.3 into 10 to the power 17 kg per meter cube, and this is almost going to be constant. That means it does not depend what element it is. This value of density is almost constant for any kind of nucleus. It is constant, right? So that means density should not change. If the density of a nucleus changes, then there will be nuclear reaction, right? Okay, then what else? And also note that density changes with radius. Density changes with radius. How density changes with radius? Note that, suppose if you consider this is the center of nucleus, so density keep on varying. If you see the graph of density versus distance from center, this density is maximum at the center. After that it goes like this. Okay, so how do we define radius? We choose a radius, distance r radius, where density become half of maximum, where density reduces by half factor, right? So at the center here density is maximum, and you take a point where density has become half of maximum. So this is what we are defining as radius of nucleus. Okay, radius of nucleus is the, otherwise still nucleus extend beyond this value also. Okay, right. Let us continue to cover the topic, because lot of theories are there in this chapter and we need to cover up, wind up this topic. So now we will understand uh, mass defect. Mass defect. What is the concept of mass defect? Mass defect. Suppose if you take a total mass of a nucleus or mass of an atom, mass of an atom is mostly due to mass of nucleus. Mass of atom is mass of electron plus mass of proton plus mass of neutron. How many electrons are there? How many protons are there? Number of electrons and protons are equal, so Z, Z. And how many neutrons are there? Neutrons are A minus Z, correct? So you can calculate, this will give us the theoretical mass of an atom. But actual mass of an atom, it is experimentally calculated. This is the theoretical mass. Theoretical mass. Theoretical mass means considering mass of all, right? Of course, if you skip the electron mass, let us consider just the nucleus formation. Okay, let us take mass of nucleus itself. Mass of nucleus, if I write, then I will not count electron. Okay, and here I am talking about mass of nucleus because electron is anyway outside. So mass of nucleus, if you actually calculate, this is the mass of nucleus. Experimentally measured will be this. So difference delta m. So first of all, you should know that the mass of nucleus, which is theoretical, theoretical, is larger than actual mass, which is measured by experiment. So why this difference is happening, where the mass is going? So that is what is called mass defect. Delta m is called mass defect. You can also count electron, but anyway, electron, there is no difference in that. That's why we are not taking electron mass. So delta m, difference of that. So mass, theoretical mass, theoretical minus actual mass. If you calculate, that is called mass defect, and mass defect comes as positive. Delta m comes as positive. Why? Because theoretical mass is larger. Where this mass is going? This mass is getting destroyed during the formation of nucleus. You need to note here that during the formation of nucleus, during the formation of nucleus from nucleons, mass is getting destroyed and it is converted into equivalent energy. So equivalent energy, how do we convert it? So conversion of energy, mass into energy and energy into mass, is given by Einstein mass energy equivalence. Einstein's Einstein's mass energy equivalence. What is that mass energy equivalence? That says that the mass and the energy is equal to mc square. Okay. See the speed of light, I mean the mass, right? So if you destroy m mass, m is here the mass destroyed, and c is the speed of light, speed of light. So we can destroy some mass and you'll get a lot of energy. So you should know that if you take mass here as one atomic mass unit, so one atomic mass unit is equal to or equivalent to 931.5 million electron volt. Okay, equivalent to million electron volt. But if you want to write equality, then you can write 931.5 by c square. Okay, that is what is million electron volt. Because when you substitute here, you will get, right. Now here we should also note that what happens if we destroy one electron. So mass of one electron can be converted as 0.511 million electron volt by c square. Mass of one proton can be converted as 938.28 million electron volt by c square. Mass of one neutron 939.573 million electron volt by c square. Okay, we must remember this. Then, what is the concept of binding energy? Let us go into the topic of binding energy. binding energy, binding energy, energy released during the formation, during the formation of a nucleus by bringing the nucleons from infinity. That is what is called binding energy. So, how do we calculate binding energy? Binding energy is calculated by delta m c square. Because if the nucleons are, like for example, suppose the protons, neutrons, protons, neutrons, they are separated, and when you try to bring them closer to form a nucleus, then we have seen that there is a mass defect. That mass defect is happening. Why? Because some energy is getting released. That is the energy difference. Okay. So of course we will calculate this binding energy in terms of whatever delta m will be given in atomic mass unit. We'll multiply with them as 931.5 and we'll get the answer in million electron volt. Right. Then what is average binding energy? Let us discuss about average binding energy. Average binding energy, or it is also known as binding fraction. Binding fraction. So binding energy per nucleon, binding energy per nucleon, that is defined as total binding energy by mass number. So which is delta m into 931.5 divided by A. That will come in million electron volt, right? Million electron volt. So this binding energy per nucleon gives one idea. What is that? Binding energy per nucleon or average binding energy gives idea of what? It gives measure of stability. Measure of stability. Stability of nucleus. Because what does it indicate? It indicates that how much how much energy is released, or how much nucleus, each nucleon is bound with the other nucleon, how much each nucleon is bound with the other nucleon. That means you can say how much each nucleon is bound inside the nucleus. The total binding energy doesn't give that idea. Average binding energy or binding energy per nucleon gives this idea. Okay, right. So if binding energy, I can write this as average also. Okay. Average binding energy is more. That means nucleus is more stable. More stable. Okay. Now there is an important term called packing fraction. Let us also discuss that packing fraction. Packing fraction. What is packing fraction of a nucleus? So this packing fraction is defined as minus delta m by A, and it is defined as then m minus A by A. What is m here? M is the actual mass of nucleus. A is mass number. M is the Mass of nucleus. Actual mass of nucleus. So actual mass A minus m, that is what is mass defect. You know that A minus m is mass defect, but m minus A by this. Okay. So packing fraction also gives measure of stability. Packing friction gives measure of stability. Measure of stability. And smaller packing fraction, larger stability. Larger stability of nucleus. Right? Packing fraction can be negative, it can be 0, or it can be positive. Everything can be there. So if packing fraction is positive and packing fraction is negative, what does that mean? Negative means it is more stable, positive means it is less stable. And if packing fraction is 0 means it is neutral, right? Neither more nor less. Example, so it is like neutral stability. Neutral stability. Neutrally stable. Neutrally stable. So example, carbon 61, for its packing fraction is almost 0. Okay. Transition elements. Transition elements or iron have lowest value of packing fraction, and that becomes maximum stability. Maximum stable. So iron is maximum stable. Okay, so I think let us keep up to this much topic. So in the next class, we can cover up the remaining topics, which is the graph of binding energy per nucleon versus mass number, and we can see more theories related with that. Then we'll go to the next topics in this chapter, right? So we'll try to cover up that in the next class. Thank you all for your attention. Let us meet in the next class. Bye bye all.